Attendees are in listen-only mode.
Greetings, everyone. I am Corey Gooker, coordinator for the Northern Rockies Fire Science Network. And on behalf of our team and our partners, I want to welcome you to today's webinar, A New Age of Wildland Fuel Science, with Bob Keane, research ecologist with the Missoula Fire Sciences Lab. Before introducing our presenter, I want to just run through a couple of webinar housekeeping items. At any time during the webinar, you can ask questions of me or our presenter by typing them into the questions pane of the control panel at the right of your screen. Following the presentation, I will field the questions that you've typed in. Whatever you do in your control panel, however, will not affect the presentation, so feel free to type a test message or test your audio anytime during this webinar. We are recording this webinar, and it will be posted on the Northern Rockies Fire Science Network website soon after the conclusion of the live webinar. And I will post that address for you. With that, I'll move on to the introduction of our presenter, Mr. Bob Keane, who likely needs no introduction. Bob's research includes developing spatially explicit ecological computer simulation models for exploring landscape, fire, vegetation, and climate dynamics, conducting wildland fuel science, the sampling, describing, modeling, and mapping of wildland fuel characteristics, and investigating the ecology and restoration of whitebark pine. Bob has developed a staggering number of simulation modeling programs, most of which are known to you by lengthy acronyms. They include CRBSUM, LandSum, FireBGC, FireBGC Volume 2, and the first versions of FOFUM. Bob also wrote several fire hazard and analysis programs, such as WX Fire and Fire Harm, and assisted in the development of FireMon and EcoData. Bob has also written numerous articles about the restoration of whitebark pine ecosystems and the decomposition, deposition, and accumulation rates of wildland fuels in the Northern Rocky Mountains. Today, though, Bob is sharing what he learned while writing his first book, at least I believe it's your first book, Bob, Wildland Fuel Fundamentals and Applications. Welcome, Bob. Thank you for being here today.
Well, thank you very much, Corey, and thank you, everyone, for attending on this wonderful morning. I really appreciate your time on this really what I feel is a really important project. What I'm going to talk about today is the fact that there are many, many challenges we have in the describing, the classifying, the quantification, the mapping of wildland fuels in the United States. And I think the traditional ways we've done and measured it need to be rethought, redone, reevaluated, and maybe it's time to usher in a new era in wildland fuel science. So when we talk about wildland fuels, a lot of people don't really understand the importance of wildland fuels to fire management. First of all, wildland fuels is, of course, a major input to most fire models. But many fire behavior models, their effects or their simulations and predictions are not, fuels are not really that highly sensitive to what really drives fire behavior. But if we want to look at fire effects, fuels are an incredibly important input that are really needed to get at fire effects and actually predict them with any accuracy and precision. One thing about fire management, when we talk about fuels, is that we have to realize that climate and all the other things that fire management has to deal with are not really under their control. But wildland fuels are under their control. So when we talk about alternatives for fire management, fuel is one of the only things that we really can control in a wildland situation. And anymore, we as fire ecologists or people in fire management can't just think about fuels in the context of fire behavior and effects anymore. We have to realize that fuels are becoming much more important to many phases of ecology and land management, and that they are incredibly important in smoke prediction and carbon dynamics, ecosystem restoration. People in the wildlife field use fuels to predict wildlife habitat. Carbon folks need an expression of dead woody fuels on the ground to make carbon dynamics work and so on. So no longer is fuels just in the domain of fire management. It really goes beyond fire management anymore and touches almost all fields in land management and ecology. So I think we can all agree that an accurate description of the fuels and quantification of the fuels that are out there is actually very essential for effective land management. So just exactly what are fuels? When we talk about fuels, what are we talking about? Well, if you review the literature at all, you realize that there are many definitions of fuels, and all of them are esoteric and very difficult to understand in any given context. But one thing we have to understand is fuel is really any biomass that's available to burn. But then we get into the discussion and debate about just exactly what is the availability. Is a stick that's in the center of a parking lot really available to burn, or is a wet fuel that is too wet for burning really available? But of course, all of these biomass types can be burned later on under given conditions as things change. So in this talk, I think we can use the equality that all biomass, whether it's live or dead, is considered fuel and can burn. So for the purposes of this seminar, I'd like to emphasize that biomass is fuel, whether it be live or dead. So let's talk about what the historical use of wildland fuels were. How did people describe fuels in the past? And when I did this research, I was kind of amazed at how people did it. If we go back to the 1920s and prior to the 1920s, Shaw and Katuk looked at this and described fuels not as a fuel bed or as what was in the fuel bed, but as hour control zones, or how long it took for a suppression force to actually arrive. So if there were light fuels that burned slowly, the hour control zone had a bigger number, whereas if it was flashy fuels and it was distant or it was very close, the hour control zone was small. So people describe fuels in a concept of underneath the context of fire suppression. This was further done, and probably one of the benchmark ways that we describe fuels way in the past was Hornby took his 60 people and went out and mapped this huge area in the Northern Rockies, and they mapped fuels, but they didn't map fuels in terms of loading or what kind of fuels are out there, whether it was woody or not. They mapped them in terms of two categories, rate of spread, and there were 4 categories of rate of spread, extreme, high, medium, and low. And they also mapped it by classifying it by eye to resistance to control. So they had maps of these 2 attributes that each had 4 categories. So they mapped these fuels not on what vegetation was there or what biomass was there, but again in the context of fire suppression. This was so successful that it was repeated across the entire United States by a wide variety of people, from the Pacific Northwest to the Midwest to New Jersey and then to the entire Eastern Seaboard, that these fuel descriptions were then mapped and described. In fact, other people then tied a vegetation type category to Hornby's classifications, and a guy, Matthews, in '37 actually developed a plot-based method to actually validate that these 4 categories were correctly called for each of the 2 attributes. So Hornby's method was repeated for over 50 years and used quite extensively in land management. Kind of at the same time, there was a group of people that were calling fuels based on vegetation, and they would talk about fuels based on the vegetation that was there. And the vegetation was more often than not talked about by the dominant tree type. So many people would talk about pitch pine fuel, or maybe longleaf pine fuel, or in this case whitebark pine fuel, to describe what fuel beds are out there. Again, they use vegetation and not the actual fuel bed to describe what kind of fuels that were actually out there. It wasn't until there was an actual application did we find that people actually looked at the different parts of the fuel bed, or what we now call fuel components. Gisborne, of course, in '36 tried to look at fuel moisture and wanted people to measure fuel moisture, so he had to describe the fuel bed based on more finer fuels like small woody fuels and flashy fuels like grass. Faunestock developed a huge key that keyed out what the fire potential was based on various attributes of both the surface and canopy fuels. And so by this, people started stopping looking at fuels in the context of fire suppression or in the context of vegetation, and we're actually focusing in on what exactly the fuel bed was composed of and how each of these fuel components influence fire behavior and spread. And of course, with the development of our complex fire behavior models that we have today, with the Rothermel, MacArthur, and Van Wagner models, we now see that all of the fuel beds are now described, both surface and canopy, in terms of the fuel bed is stratified by fuel components that are then based on how they are input into the fire behavior model. So these applications actually drove us to actually look at the fuel components in greater detail and allowed us to describe the fuel bed in a more comprehensive fashion. So what are these stratifications that now exist in our fire behavior modeling parlance? Well, we often talk about surface fuels, which are those that are less than 2 meters above the ground. Canopy fuels are those biomass that's greater than 2 meters above the ground. And of course, ground fuels, which are those fuels that are below the little layer and into the soil that are organic biomass that have been decomposed. Then we look at, those are the different fuel strata. Then we look at if they're live or dead. And of course, live fuels lose moisture and gain moisture much differently than dead fuels do. And then in fire behavior stratifications, there are woody fuels, and then there are shrub, and then there are herbaceous. And then on the ground, there's both litter and duff. And of course, litter is a surface fuel, duff is a ground fuel. And then we divide up the woody fuel by 1, 10, and 100-hour time lags. And these are often than not, the inputs that go into many of our fire behavior applications and also fire effects applications that we have today. An important point here is that these components are defined for inputs in the fire behavior models, which means that they were designed specifically so we could model fire behavior. And let's not forget that each one of these fuel components has multiple attributes. We can talk about loading, which is far and away the most important attribute, but there's also its moisture content, its mineral content, its surface area to volume ratio, density, and so on. And so each fuel component has a wide variety of fuel properties. So the take-home message with this little romp through history is that when we talk about fuels, and we talk about the fuel bed, and we talk about the components that comprise the fuel bed, all of these were defined and studied in the context of fire behavior. This is nothing new, and it's nothing, this is one of those, yeah, no kidding, fuels are what's going to burn in the fire model. But what I think, and what we've happened, is that one of the reasons we need to usher in a new era in fire behavior and in wildland fuel science is because we've always looked at fuels through the lens of fire behavior. The reason I think this is because in 2006, the Missoula Fire Sciences Lab started a wildland fuel science research program using National Fire Plan monies, where we conducted research to develop new technologies in wildland fuel science. What we tried to do is expand the technologies that we have now in wildland fuel science, compare them with what we have now, and move forward to get better, more effective, more accurate fuel sampling techniques, fuel classifications, fuel maps, and so on. And what we noticed is that most of our current technologies and fuel estimates were incredibly inexact, and that our classifications and many of our fuel applications were often ineffective. And this made our fuel maps quite inaccurate. And so we noticed that there were many problems with the current fire technologies that we have to revisit and find out just exactly why these things were going wrong. So in the end, what the conclusion was is that we've been kind of doing it all wrong. If we want to make the most accurate and most effective fuel application, we really have to take an ecological approach, and we can't only look at fuels through the lens of fire behavior. We have to merge fire behavior with an ecological approach. So what I'd like to talk about in the next 20 or 30 minutes is I'd like to present around 7 studies that we've done with that National Fire Plan money that present some of the major reasons for the failure of the current technologies. And then for each one of these studies, I'm going to discuss its implications. And because they fail, or because of these things, what the implications are to fire management. And then I'm going to use all the results of these studies to explain just exactly why we need to usher in a new era in wildland fuel science. So with that, I'm going to go with our first study. And the first thing we noticed when we started to do classifications and we started to do fuel mapping and started looking at fuel data, we noticed that, holy smokes, there is a lot of fuel components that are missing in the current quantifications of fuel beds and the descriptions of fuel beds. We know a lot about dead and live crown foliage, biomass, and branchwood, but we have no real way to get at arboreal mosses and lichens, and those things kind of fall through the cracks. We look at live and dead shrub or herbaceous, and we group them into life forms, whether they're shrub or herbaceous. But we notice that there are huge differences between shrubs, and there are huge differences between the herbaceous material that is underneath in the surface fuel layers. For instance, a curing grass will behave quite differently from things like Balsamorhiza sagittata, which has a huge, large leaf. There are great differences between shrubs and herbaceous that need to be described. We also notice that while a lot of people go out and sample live shrub and herbaceous, they miss the live and dead tree regeneration. And then also the way we look at logs is quite stunning in that we say all logs are above 3 inches in diameter in fire management and fuel science. But we know that a 20-inch log will decay as a completely different set of attributes, quite different from a 3-inch log. And of course, on the ground, we look at the down dead woody, twigs and branchwood, and we divide them up into 4 uneven classes based on their diameter, size classes. But we don't really have methods, and we haven't really described other things on the ground other than twigs and branchwood and the litter and duff. We don't really look at cones or buds that are on the thing, or mosses or lichens. And there really isn't a way to get at them very quickly. So a lot of the fuel beds that have been described in the past are missing these very important biomass types. And of course, what this means is that we're always going to get lower estimates because we're not including those biomass pools in our smoke estimates. And of course, if we're going to predict soil heating, we're going to inaccurately predict soil heating. And then of course, by missing those, there are going to be some of those, like tree regeneration, that are going to contribute to fire behavior that we're going to not have in our fire behavior estimates when we put in our fuel inputs. And of course, by missing all these components, we're not going to get good estimates of fire effects. Another study we did is we went out there and we actually looked at the variability of fuels within a 1-by-1 kilometer plot. And we did pretty intensive sampling, and we did destructive sampling, where we actually picked up the fuels and measured them, their dry weight, in the lab. And what we noticed that if we look at the x-axis, which is particle diameter, and the y-axis is coefficient of variation. Coefficient of variation, as a review for some of you, is the variability of an item expressed as a percent of the mean. So a 200% coefficient of variation would mean that it is twice the size of the mean. So if the mean was 10 kilograms per square meter, the variation would be 20 kilograms per square meter. So what we have here is what we found is that there is a huge amount of natural variability out there in fuels. And this amount of variability actually increases in particle diameter in a statistically significant fashion. Is that we get increases from about 100 in a coefficient of variation to over 800 for our large woody fuels. This means that there are a lot of natural variation out there that we must be able to quantify if we're going to actually describe fuels in the future. And by ignoring it and simplifying fuels, we are kind of missing the entire picture of how fuels are laid out on the landscape. When we actually dove into this variability, we found that this variability is highly skewed. It is not normally distributed. And this is because a lot of the estimates of fuel at the microplot level have a lot of zero values. So the skewness is often to the left. This makes using parametric statistics incredibly difficult and questionable. whether you can actually use parametric statistics in a statistical analysis of fuel conditions. So the implication is that any attempt at simplifying fuel beds is going to ignore this amazing natural variability. Most studies in ecology look at CVs that are around 20, but us in fuel and wildland fuel science are looking at coefficient of variations that are between 100 and 800. So we must include this variability in any application that we do. And of course, this variability compromises the accuracy and precision of our fuel products. And if we don't include the variability, we're always going to miss. We're not going to be able to specifically define what the accuracy of our fuel products are. And of course, the skewness compromises any attempts, or compromises a lot of our attempts at using parametric statistics to look at how fuels change over time or whatever. Another study that we did, we went out and we looked at how fuels vary over space, how that variability is distributed over space. And we use these complex spatial statistics to do, but what I'm going to talk about today is a thing called the range. And the range is what often is referred to as the inherent patch size. And what the range means is it's the size of the area at which you get the maximum variability. If you sample an attribute at anything less than the patch size or the range, that means that you're not including its entire range of variability in your estimate. So you're automatically introducing uncertainty and error into your estimate. And what we found was if we looked at the particle diameter, or the diameter of the fuel particles, we see that the patch size varies from 1 to 5 meters at our smallest, liter and 1-hour fuels, to over 150 at our largest logs. So this means that the way fuels are distributed across the landscape are inherently different between fuel components. Is that we can't assume that we have the same distribution for logs as we have for 1 hour and 10 hour. This is incredibly important because all sampling efforts must account for scale, and most of our sampling efforts don't. We often use the same scale of sampling for both the 1 hour and 10 hour as we do for the 100 and 1,000 hour. So a lot of our sampling efforts are compromised because we don't realize that our fuel is distributed across the landscape in different patches. And also, we have to realize that a lot of people, there are a lot of research, especially in the three-dimensional fire modeling, have noticed that the spatial distribution of where fuels are affects the way fires burn and the way effects happen. So these spatial distributions are very important if we want to predict fire behavior and effects better. The next study we did was a 15-year study where we summarized the temporal variability of fuels. We actually put litter traps out there at different sites across the Northern Rockies. We had 28 sites, and we sample or emptied these litter traps twice a year, and we found some pretty interesting results. Is that if we look in the top right, we see the mean annual foliage rate of deposition, and we see over the number of years that we actually sampled. And what we see is that foliage really doesn't vary year to year. It pretty much stays the same 1 year after the other. And you'll get years that are higher, years that are lower, but they're statistically not really significant from each other. But as we go up in fuel size, we see that the variability, year-to-year variability, will increase as we go up in fuel size. And you'll see the larger fuels, like the 100-hour in the bottom right, has a big event where all this 100-hour fuel hits the ground in probably a wind or a snow event. And that all the years after this happens, you have relatively little 100-hour fuel hitting the ground. So in other words, not only are fuels spatially different in the way they are distributed all across the landscape by fuel component, but they're also temporally variable, and the variability is different by fuel component. The next thing also we noticed is that if we look, we took and had decomposition bags out there for 15 years, and we noticed that, sure enough, each fuel component that we have in fuel science also decomposes at different rates. This is incredibly important. You know, there's 4 Ds that dictate fuel dynamics: vegetation development, decomposition, deposition, and disturbance. And if each one of these varies by fuel component, this makes quantifying fuels incredibly difficult. So the implication is we have to accept and embrace the fact that fuels are inherently variable both in space and time, and they change rapidly at different rates. And so if we want to design sampling methods and monitoring methods, we must be able to account for those changes. Another study we did is we went and took 1,000 or whatever plots, and we said, you know what, do these fuel components correlate with each other? So we looked at the surface fuel components that we had, the 1, 10, 100, shrub, herbs, duff and litter, and logs, and we said, are these correlated with each other? And this really rocked my world, as we found out that they really weren't correlated with each other. This is a matrix of the Pearson correlation coefficient, so it isn't the R squared, it's the R, and the highest R is 0.408 for 100-hour to 10-hour. And it's statistically significant as indicated by the 3 asterisks. But the correlation is extremely poor at 0.4. Now, many have assumed that if there is a change in 1 hour, there must be a change in 10-hour, and there must be a change in 100-hour. Because you would think that because plants have allometry, or their branch patterns are related to each other, that would be the same way on the ground. But what we found is that that is just not the case, that all these fuels vary independently. And it's, of course, due to the 4 Ds. And the 4 Ds dictate the fuel dynamics on the ground. So what we found is that surface fuels don't correlate with each other. And not only that, we also did it with some vegetation attributes, species, so on, and we had about 22 attributes for the vegetation, and you're seeing the 7 that had the highest correlations. And we found that none of the surface fuels correlated to the vegetation characteristics. None of them correlated to species, and then if we look at all the others, there's very poor correlation. So this is another thing, is that surface fuels are not highly correlated to vegetation characteristics. Yet, look at all of our fuel classifications that we use in historical times and also today. There's a lot of them are based on vegetation. Luckily, a lot of our canopy fuel characteristics do correlate to our vegetation characteristics. So we can use vegetation as a surrogate for canopy fuels, but we can't use vegetation as a surrogate for surface fuels. This means that you can't really assume that the surface fuels, if one surface fuel component changes, the others will change. And you also can't use vegetation to really describe fuels. That each fuel component varies independently, and that this makes classification, mapping, and everything very, very difficult. If one of the benchmarks to classification is that if one fuel component goes down, then others have to go up, and this we found just isn't the case. Another study we did is we took a look at, we actually tried to invent new technologies for sampling fuels, technologies that we hoped would be quicker, faster, and more accurate for land managers or fire managers. And what we noticed that is when we compared it with the current technologies, I'm hoping that all of you can see this pointer in the field, that we found that if we compared current technologies with more research-related fuel sampling techniques, that there are many problems with the way we sample fuels today. The first 4, in each of these graphs we see that the y-axis is the estimated biomass, and then we have a number of different ways that we sample the fuels in a particular sample bed. Now, we knew exactly what the loadings were because we actually created these fuel beds in the parking lot of the fire lab. So that is the horizontal line that we see on the picture that goes up. So this upper left-hand graph has a reference or a truth at 0.05 loading. And then we looked at all of these different fuels and how they performed. The dot represents the mean that we sampled, and the bars represent the standard error. So obviously, if the bars are within the line, that means that the sampling method is acceptable. If the mean, the dot, lies on the line, that means that the sampling method is really good for that particular loading. First thing I want you to look at is the first 4 categories, and these are the planar intercepts. And this is the planar intercept, of course, is the Brown's transects that many of you have done. And PI means planar intercepts, and M means measured. And this is where, instead of actually going to the 1, 10, and 100-hour category, we actually measured the diameter. And if we measured the diameter, we got accurate planar intercept estimates. But PIT means using the traditional 1, 10, and 100-hour classifications. And you can see not only for the 0.05, but for every loading, the traditional way that we sample fuels ensures, because of the uneven fuel size categories, that ensures that we'll always get the wrong answer. So we found that if you use the 1, 10, and 100-hour classifications, it performs quite poorly. We looked at just going to the 1 centimeter classes, and this was acceptable. But if we went to the 2 centimeter classes, which is the PI 2 centimeter, we see that it was poor. So any attempt at trying to sample with 1, 10, and 100-hour fails because, of course, for instance, the 100-hour category goes from 1 to 3 inches. And since volume and therefore loading varies by the square of the diameter, you can get an estimate that's between 1 and 9 times off. So you can see why these things fail. All of the rest of these, except for the last one, which is the photo load method, which is the method that we developed, all of these other ones are what we use in research, which are fuel microplots. Notice that all of the fuel microplots, which FMs, have a huge range of variation, and these actually capture the range of variation that's actually out there better than the planar intercepts. And notice where the fuel microplots fail is when we use the traditional way of sampling fuels. Notice that photo load did well at the beginning when there were light fuel loadings, but poorly at the end when we had jackpot fuel loadings and the fuel loadings were high. So the take-home, then what we found also is when we did statistical analysis, we found that you needed 800 meters of line in our little plot for planar intercept to get an estimate that encompasses the variation, the natural variation that was out there. And we only needed 18 microplots to do this below. And so we traditionally undersampled our ecosystems out there, and we included a lot of error because we were unable not only to get at the true variation because we were using the 1, 10, and 100-hour categories, but because we didn't sample the full range of statistical or spatial variability that was out there. The take-home message here is that it is very difficult to get an accurate estimate of fuel loadings using traditional components. Historically we've been sampling at suboptimal intensities. It's not that the way we've been doing it has been wrong. It's just we have to recognize that we really hadn't sampled it to enough to actually quantify the natural variability that's out there. All of the things I've talked about are some of the reasons why our classifications that we use in fire management have performed poorly. We could only evaluate 3 classifications because these classifications were based on either the fuel bed characteristics that are out there or the vegetation that's out there. We could not evaluate the performance of fire behavior fuel models like the Scott and Bergen 44 or the Anderson 82, Anderson 14 or 12, because they have no key that will positively and consistently identify it on the ground. So we could only we were limited by these 3 classifications. The first is the FLM, the fuel loading models. The second is the FCCS, which is the fuel characteristics classification system. And last is a classification system that is used by some of the smoke people that Sean Advansky developed that is called a fuel type group that is correlated to a forest type group based on FIA classifications. So the first one is based on a fuel component key. The other two are based on vegetation. And what we did is we had 14,000 FIA plots. We went out and keyed each one of these classification categories based on the FIA plot characteristics, and then we compared the FIA plot loadings with the classification loadings. And you can see that while the FLM performed probably the best based on the R-squares, which should be near 1, and we see the R-squares for duff and coarse woody debris, that's CWD, is close to 7 or 8, and the slope should be around 1. The intercept should be 0, the percent bias should be 0, and the root mean square should be 0. And you'll notice that litter and fine woody debris, or FWD, correlate poorly with the fuel loading model. And the reason, of course, for this is because the fuel loading model key concentrates on the duff and the coarse woody debris, and more or less doesn't include a lot of detail in the litter and fine woody. The FCCS is based on vegetation characteristics, and it performs poorly because vegetation characteristics aren't really correlated to fuels. And of course, the way we did this is not really the way FCCs were envisioned to be used. We had to use an FCC fuel bed that was used in land fire. And it's really important to know that FCCS is really, the way we're using it here really isn't what it was intended at. But the FTG was intended to be used for this, and you can see it has a poor performance as well. Here are the regression curves on here for the FLMs. You can see the horizontal cluster of points indicates that you have one loading for the FLM category, which is the FLMs are on the vertical axis, and on the x-axis is the range of loadings for that particular category over all the FIA plots. And you can see the huge range of natural variability within each of the FLM categories. And you can see why it's so tough, because of the huge natural variability, to actually key to a correct fuel loading for that FLM component. This is the reason why fuel classifications are so hard to do, is without embracing the natural variability that's out there, it's going to be difficult to actually use classifications as inventories to get at any estimate of fuel loading that's actually close to what is out there. There really isn't any representative fuel bed that we can use. So we really must either include this variability in our classifications or evaluate each fuel component individually. Then we looked at fuel mapping, and of course we looked at fuel mapping, the land fire fuel maps, which are a lot of people use, and we still use, because we had FIA plots that we could key to these, what we call fire effects fuel loading models, the FLMs, the FCCS, and FTGs. We expected fuel maps to be great until we realized that the performance of the fuel classifications were poor. So how in the heck could we expect the maps to be great? So if the classifications are poor, the maps are going to be poor. But also we have this other thing involved in there, is that we have the fact that when we mapped it, we're mapping at a 30-meter pixel level, and this is not the scale at which most fuels vary across the landscape. So not only do we have the fact that the classifications didn't embrace the natural variability that was out there, but they also, the mapping didn't match the scales to which fuels are distributed across the landscape. So it was difficult to match the imagery, the ground truth data to the map. So those are the studies we used, and we finally realized that, you know what, we really need to rethink the way we're doing fuels in the future. Is that we just can't go and start developing new technologies that will be as ineffective, or that won't be as effective as we really want them to be. And we noticed that there are many challenges with describing wildland fuels, but one of the major sources of error are that we continue to describe fuels in the context of fire behavior. We tend to try to simplify fuels. We tend to develop fuel components that are specific to a fire behavior application. And by doing this, we're going to ensure that we continue to have high uncertainty and high error in our estimates of fuel loadings on the ground. So if we really want to attain, when we want to be more effective in the future, if we really want more accurate, robust fuel information, we really need to usher a new level of wildland fuel science by taking a more ecological approach. Now, the first thing a lot of people are going to say is that, hey, I bet we can improve the performance of the existing technologies. And yes, I think we can as well. And there are many short-term fixes that we can do to increase the performance of our current fuel applications. Many of us agree that the research's standard reply is always more data. We can take more data and get more better results. We can reanalyze there are new statistical methods every day that we can take and redo and get better analysis results and better and reduce our standard and our errors in our estimates. We can add more classification categories, or we can stratify our analysis and key classification categories based on ecological regions or geographical reasons, or maybe even biophysical descriptors like elevation. And we can tune our classifications and our maps based on that. But all of these, I believe, will only result in minor gains in performance. I think that if we really want to be serious about getting accurate applications in the future, that real gains in performance will only be achieved through a new exploration of wildland fuels. And we really need to understand wildland fuel dynamics by conducting fundamental fuel science along with fire behavior science. Then we can develop all of our new fire fuel sampling techniques, or maybe we will update old techniques, and we can describe fuels in a different way and so on. A lot of people may think that this will result in more difficult ways to get at fuels in the past, and I would disagree. Is that this actually may make it simpler in the future to go out and get fuel inventories. So the future I see is that we need a fully integrated approach where the wildland fuel science integrates ecology of fuel beds with the physics of fire behavior. If you will, the ecologists are walking hand in hand with the fire behavior folks in the development of the new fire behavior models and in this new field of wildland fuel science. So what are the examples? What do we need to do in the future? For instance, one of the big things is let's use actual diameters and not time lag classes. We can immediately improve our estimates. Let's differentiate between species, not only in the shrub and the herbaceous fuel components, but let's differentiate between species in the logs, and maybe even the 1 in 10, 100 hour. A lot of our error that we have in loadings is because we assume a constant density. And so by stratifying by species, we can get density estimates a lot better. We can include all the fuel biomass categories and embrace the natural variability that's out there and recognize that fuels are inherently dynamic in space and time, so that we can include the spatial and temporal scales in this. Here's an example, is that if we use 1 centimeter diameter classes, we will get more accurate fuel estimates, even with the existing technologies. And this will mean that we'll get more effective fuel classifications and more accurate fuel maps, and it will enhance our ability to simulate fuel dynamics. A lot of our fire behavior, risk, and hazard analyses often assume a static fuel bed. By looking at 1 centimeter diameter classes, we can get better estimates of deposition and decomposition, and we can change these fuel beds better in the future by putting in ecological models that simulate deposition and decomposition and disturbance and development. So I want to emphasize that all of what I've said does not mean that the current classifications in MAP are not useful. They are very useful, and they're the only ones out there, and they represent the current state of the science. But it is important that we, researchers and managers together, recognize that there's a lot of inherent uncertainty in these predictions and applications that we're currently using, and that when we interpret the results, we must take into account the high natural variability of fuels, both in loading and their other characteristics, and how they're distributed in space and time. But in the future, I guess we need to start thinking about ushering in a new era in wildland fuel science. And I'd like to end on that. If you are really interested in this, as Corey mentioned, there's a new book out that I wrote, called Wildland Fuel Fundamentals and Applications, and a lot of the principles that I've mentioned here today are in this book. I want to emphasize that I get not a red cent from this book, and it's not really an advertisement. It's more of a here's a new source of information thing. As a matter of fact, Springer has told me that all the royalties that would have been gotten are going to go to actually reduce the price of the book. So if more people buy it, they actually told me that the price of the book, and all of the things that I talked about today are in this book. So with that, I'd like to end the discussion and accept any questions.
Well, Bob, as always, you were so thorough and systematic that I see no questions here. But I have one for you. My question would be, where are you in this process of the new era of fuels science? Are you currently working on this question? Is it focused on better characterization of the fuels using the same fire behavior models that exist, or is it better characterization of the fuels and a new fire behavior modeling system that can get at that high level of characteristics of the fuels?
Okay, so the Wildland Fuel Science program was defunded in 2013 or 12, and Colin Hardy, the program manager for the Fire Fuels and Smoke program, has patched together a ton of funding to keep this program going. And so we are still doing fundamental fuel science research, but not at the level we need to do to really usher in this new level. But I am not advocating that only the Fire Lab do it. I am thinking that many people need to help. We need a lot of help to get this done. We need help to quantify the decomposition of each one fuel particle by species. We need help to look at how fuels are distributed on the ground and what are their characteristics and attributes. For instance, I firmly believe that there are characteristic fuel loading curves by diameter size classes, which means that in the future we may only need to count the number of fuel particles because we can infer a diameter loading distribution. And so it may, we need people to do that work. And so where we are is we are trying to go, so all of from 2000 to 2012 was the realization that we need to kind of step back and start from the beginning. And at 2012, we tried to start back from the beginning, but there's not really a lot of money there. But again, is that I'm not saying that it should be just us. It should be everyone should realize this and recognize it as a new research direction.
How far do you think we are away from the level of understanding that you think would significantly improve fire behavior modeling and risk analysis?
Oh, we are decades from it being adopted by management. We're probably 10 years from it being adopted by research. Yeah, we're a long ways away. But on the other hand, we're at the same level of understanding as many fire behavior efforts. And so it may be that in the future we can, we are kind of can go together and maybe help each other along. And the ecologists can help fire behavior people, quantify components more ecologically so that can be sampled and modeled more effectively. And the fire behavior people can tell the ecologists, hey, this is what we need. How would you do it?
Well, you didn't get any new questions, so I guess that will close the webinar. As we do close the webinar, a brief 3-question survey will pop up, and we'd really appreciate your feedback. If you have questions regarding this webinar or you have any requests for future webinars, you can email or call me anytime. And I just want to thank everyone for your participation today. Thank you, Bob, for a great presentation. Everyone have a great rest of your day. Thank you.